Edexcel Core Pure Calculus 5 Integration Techniques. Substituting x equals a sine u or x equals a tan u. We should already know some substitutions that are worth considering. For example, if we are dealing with expressions with the square root of 1 minus x squared, it's worth considering x equals sine u, or 1 plus x squared, x equals tan u. And we can extend these ideas that if we are dealing with an integral involving the square root of a squared minus x squared, then x equals a sine u is worth considering, or if it's a squared plus x squared, then a tan u would be worth considering. And the reason being that a sine x squared plus a cos x squared, if you pull out a squared as a common factor, you get a squared times sine squared plus cos squared, which is a squared times 1. So if we look at this definite integration first, 25 minus x squared, in order to make full use of the previous techniques, we need to let x equal 5 sine u in a situation like this. dx by du is 5 cos u, and therefore we can substitute for dx. Don't forget we need to substitute for the limits as well. So we need to ask ourselves, when x is 0, what would u be? When x is 5 over 2, what would u be? So when x is 0, we'd need sine of nothing to get to the 0, u would be 0. And if x is 5 over 2, then sine u is a half and u is pi by 6. If you want to call the original limits x equals, as a little remind you, that's a good idea as well. So this is going to become the integral from u equals 0 to u equals pi by 6 of the square root of 25 minus 25 sine squared u. So you can see why we wanted x to be 5 sine u, so we got this 25 being repeated, times, and dx is 5 cos u du. So now we can think about simplifying this integral. So that's 0 to pi by 6 of, we can pull out 25 as a common factor outside the square root, so that becomes 5, the square root of 1 minus sine squared u times 5 cos u du. So we've got 5 5s are 25, so I'm going to put that nice and neat outside the integral sign. And the square root of 1 minus sine squared u is of course cos u. So we've got cos u times the second cos u du. So the integral we now need to solve is the integral of 25 with limits 0 to pi by 4, 25 times cos squared u du. So the integral has certainly changed significantly, but it's now in a form where we can have a go at continuing and completing the integration. So the integral we started off with, we've just shown, can be written as 25, the integral from 0 to pi by 6 of cos squared u. And again, the problem we've seen before is if you've got a squared sine or a squared cosine, we need to exploit the fact that cos 2u is 2 cos squared u minus 1. So using this to get cos squared u. So this will become 25. And if I rearrange this for cos squared u, we get cos squared u is a half of 1 plus cos 2u. So I'm going to put the half there and change this to cos 2u plus 1. So we don't have the problem of the squared trig ratio anymore. So we can get 25 over 2. Integrate cos 2u is a half sine 2u. Make sure you balance it up with the half. Integrate 1 is u, and now we can just sub these limits in. So we've got 25 over 2. Subbing in the top limit is a half sine 2 lots of u, so that's pi by 3, plus u is pi by 6, and then subbing in the bottom limit is 25 over 2. Sine of nothing is nothing, and u is nothing. Make sure you sub in that bottom limit, even though it is obviously going to give us the answer of 0. And then once we've tidied this up, we get 25 over 2, and we get sine pi by 3 is root 3 over 2, and the times by the half. And that answer's fine, but if you wanted to just pull out another cofactor, you could write it as 25 over 4, root 3 over 2, plus pi by 3. So looking for the key features, this 25 minus x squared is why we're using x equals 5 sine u. Don't forget to substitute for both of the limits. And this rather tricky looking square root has simplified right down to just 5 times cos u times by the other 5 cos u. So in this example we've got two things we need to do. We need to show that the integral can be rewritten as a third the integral of cos u du, and hence that should allow us to be able to complete the integration. The first problem we've got is that that coefficient of x squared isn't 1. So the first thing I'm going to do is to pull a 9 out of this bracket in order to make it a 1x squared. So it's going to become the integral of 1 over, I'm going to pull out a 9, so I'll leave a 9th plus 1x squared, which is the advantage I'm looking for, to the power 3 over 2, and that will simplify now to the integral. So this 9 here, this 9 to the power 3 over 2 becomes a 27, so there's a 27 and a 9th plus x squared to the power 3 over 2 dx. So now we are ready to make a substitution. The 9th plus x squared means that we need to let x equal a third of tan u. Differentiating this, dx by du is a third sec squared u. I'm going to pull the 1 over 27 out of the integral just to make things a little bit clearer, and this will become 1 over a 9th plus x squared, which is a 9th of tan squared u to the power 3 over 2 times dx, and dx is going to be a third of sec squared u du. So it looks fairly complicated at the moment, but it will all make a bit more sense. Let's leave the 1 over 27. What I'm going to do now is pull a 9th as a common factor out of this bracket, but it's a 9th to the power 3 over 2. So the 9th to the half is a third, cubed is 1 over 27, and that, don't forget, is in the denominator. So when we simplify this, it will be a 1 over 1 over 27, which is just 27, and what we are left with in this bracket is just 1 plus tan squared u to the power 3 over 2, and there's still a third sec squared u du. The 27s and the 27th cancel out. The third I'm going to pull out of the integral so it's nice and clear, I don't lose it anywhere. We've got a sec squared u in the numerator, and if you have a careful look at this denominator, 1 plus tan squared u is sec squared u, and to the power 3 over 2 is sec cubed u du. This cancels down to 1 over sec u, and 1 over sec u is of course cos u. So we've done the first part of the problem, which was to rewrite the integral as a third cos u du. So just picking out some of the key steps again here. This 9x squared could cause a bit of a problem, so I've pulled a 9 out of that bracket to leave a ninth plus 1x squared. The ninth plus 1x squared then suggests that x equals a third of tan u would be a good substitution, and then this term here to the power 3 over 2 will simplify significantly, and we end up with the required integral. So all we've got to do now is integrate cos u with respect to u. So when I integrate it, I get a third sine u plus c. But the problem we've got here is I need to be able to substitute back, and all I've got to work with is x is a third of tan u. So we've got to find a way of being able to substitute back for x. If I just times through by 3 to make things a bit clearer, so 3x is tan u. It is helpful to use the fact now that sec squared u is 1 plus tan squared u, so that's 1 plus 3x squared, so that's 1 plus tan squared there. Therefore sec squared u is 1 plus 9x squared, and therefore sec u is the square root of 1 plus 9x squared, and therefore cos u is 1 over the square root of 1 plus 9x squared. So there's a lot of effort needed here to be able to substitute back for x. We know that sine u, which is ultimately what I'm looking for, is tan u times cos u. So sine u is tan u, which is 3x, and cos u, which is 1 over the square root of 1 plus 9x squared. So finally we have something that we can substitute for sine u. So the answer becomes a third of sine u, which is 3x over the square root of 1 plus 9x squared plus c. Which means the original integral that we had, which integrate 1 over 1 plus 9x squared to the power 3 over 2 dx, can now be written as x over the square root of 1 plus 9x squared plus c. So just to summarise a couple of key points, the problem wasn't integrating a third of cos u, the problem was how we're going to substitute for sine u and get it back in terms of x. Well, we know that tan u was 3x, and we can use this useful identity to find sec u. So we got sec u in terms of x, and once we reciprocated it, we had cos u. So we've got tan u and cos u, and by combining cos u and tan u, we got to the sine of u, which allowed us then to finish off the integration. So in summarising some of the ideas, so in general, if we see integrals involving the square root of a squared minus x squared, then it's worth considering x equals a sine u, or expressions involving a squared plus x squared, it's worth considering x equals a tan u as possible methods. The resulting integral may need a further technique, so don't be surprised if, for example, you need a double angle formulae in order to simplify it, or something like sec squared minus tan squared equals 1. And if you are transforming back to the original variable, make sure you do it with some care, as we saw in this example. Going back to the original variable can be straightforward, but it can also be quite a tricky thing to do. And if it is a definite integration that you've been given, do not forget to change the limits before you do carry on with the integral. So that brings us to the end of Calculus 5 integration techniques.